it's only one. That's one molecular orbital, right? So this one is how many? Just one molecular orbital, right? They're all connected, right? So one more time to understand it, I guess I do something funny. Comma knows ridiculous. But anyway. So in other words, here's 1, 2, 3, 4 separate atomic orbitals. Here's one molecular orbital. Make sense? Yes? So that's molecular orbital. That's a molecular orbital. This is a atomic orbital. Okay, alright, so let's continue. So here's 1, 2, 3, and 4. And you know, you've seen me in the lecture not drawing this, should have been nice and beautiful, but now you can see how fast you can draw them, right? I mean, it's not that bad. So here's 2 nodes, yes? And then you have this, and then this, and then this, and then this, right? They can be black, where black is white or white is black, it doesn't matter as long as you have 2 nodes. And then that's by 3, and then let's do by 4, and here is 1, and then these are connected to. Okay, and then this is, again, they're all connected, right? Okay. Okay. And so now, how many nodes here?
3.
1, 2, 3. So this could be like black, white, black, white, right? And then of course, black here. Okay, so I start with 4 atomic orbitals. I start with 4 atomic orbitals separated, and then I create 4 molecular orbitals together. Of course, these are all molecular orbitals. Okay? All right, and so this pertains to this situation here. Right, so this whole thing pertains to that. So let's do this situation here. Okay, how many, and by the way, I mean, you know, this is like 1, 2, 3, 4, 1, 2, 3, 4, right? This is where this is coming from, right? 1, 2, 3, and 4. Okay. All right. And now we have the 5 and 6, and here we know that we have 2 of these. Oh, by the way, we didn't fill them out. You know, so instead of doing this, you can also simplify to have boxes, right? Yes. Here's one box. Right, so that's just a simplified box, right? Yes? And how many electrons do I have? 1, 2, 3, and 4. Now, if you were going to do the molecular orbitals for the whole compound, you had to do this, and here is like 1, 2, 3, 4, 5, 6, right? So many bonds, right? We ignore. All of these are below here, right? Right? Yes? So we just concentrate on this and this. Okay, we don't even talk about this one. That's a sigma bond, right? That's the extra bond. So 1, 2, 3, 4. So we need 4, and here they are, right? 1, 2. So this is the Pauli exclusion and the Hund's rule. You know that. I mean, actually, we don't see the Hund's rule here. It's just the Pauli exclusion. Okay, that they have to be opposite spins. Okay. So speaking of, I need more space here. You know. Okay, so this is molecular orbital, this is molecular orbital, this is molecular orbital, this is molecular orbital. So this, the bottom P1 is occupied or unoccupied? Occupied. What about the top? Occupied, the top is unoccupied, this is unoccupied. And which is the highest of the occupied? This one. Which is the lowest of the unoccupied? This one, right? So this is the ones we care about. The others, we don't really need them, right? Yes, okay. You still keep them drawing them, and you don't see like an always they're the home of the loop because that's how much we use. Okay, so let's look at the green one here. So how many balloons do I have for this one? 2, right? I have because this has the 5 and the 6, right? Yes. Okay, so we have. So the way you can combine them is this together, and they have to have 0 nodes, right? That's it. And what is the other possibility? Is to have them as 1 up and 1 down, right? So this, and they're connected together. And again, this is the pi 1, and that's pi 2, right? Star, right? By the way, here we should put stars too, 3 and 4. That's the end of one, right? Yes. Right. So when you have 4 or 6 or 8, half of them are bonding, the other half are unbonding. Here you have two, one half each of this, bonding. Okay, and then let's simplify it again. Let's have boxes here. Here's one box, here's another box. And again, how many electrons do I have? Let's go back to this molecule. Two that we're talking about, right? The extra bond. So here they are. So is this a molecular orbital? Yes, it's a molecular orbital. Yes. Is the bottom one occupied? Yes. Is the top one occupied? Yes. What's the highest? There is no other one. Just the highest is the only one, right? That's the highest occupied, and this is the lowest. There is nothing else, right? Yeah. Okay. So I use the analogy here. I use the analogy that you have buckets with water or people in apartment buildings, right? So in other words, if you want to jump from this building, from the red to the green building, you have to go from the highest energy to the lowest available. The highest occupied to the lowest unoccupied, right? Makes sense? So you just take this and you move it over here, okay? So how does this look in terms of this reaction? So in order for this reaction to take place, without light, if you use light, it's like using the elevator, right? Things can jump to higher levels, yes? So I'm gonna take this, so really we're gonna zoom into this, and we're gonna zoom into this. And let's draw this molecule. So I'm gonna take this, the red circle, and copy it, and so copy it over here, over here, over here, and over here. And I'm putting it in angles so you can see everything like the molecule, right? So this is, okay? And so you can see, right, this is like SCs, right? This kind of looks that, so I'm taking this. So according to this should be black, right? Right? And this. And again, it doesn't matter because I can do it, right? I mean, I can do, I hope you agree that this can be black, black, white, white, right? It's the same idea. So, I mean, I guess I copy the same way, it doesn't really matter, right? Okay. And then, what about if we do this, right? So we have this, we have it over here, and we have it over here. So again, this is, let's call this 6 and 5, and let's call this, 6 and 5, and then let's call this 6 and 5, right? And so this is that. Okay, and this is this. Okay, all right, and then this is the 1, 2, 3, 4. I mean, you can call this 1. Doesn't really matter because how we call it 1, 2, 3. Okay, I mean, I guess I can start calling this 1, 2, 3, 4 this way. Doesn't matter. Okay, so then if you can see, and then this is connected, right? And so the question is, you can see that these things are aligned, right? Yes, and then these things are aligned, right? Because let's say we attack from the bottom, right? Attack from the bottom. Attack from bottom. I mean, just like here we play with grammar. I mean, vocabulary, right? Attack from the bottom, really. Is the red one attacking the green one, right? So it's like saying, let's use the word bottom, right? Meaning the green one is being attacked from the bottom, right? So, well, I mean, the green one comes from the bottom, that's what I'm saying. So the better word grammatically comes from the bottom, right? The red one is the one who really attacks. Let's just use the word bottom, let's use that. It's really, if you say from the perspective of the red, it's attacking from the top. From the green is from the bottom, right? Maybe if it will be a little bit more precise, we can say dying of file attack from the bottom. That's right. All right. And so if this comes, the green is from the bottom and the red is from the top. The bottom of the red and the top of the green align, black and black. Right? So if you look at 4, same thing. The bottom of the red and the top of the green are aligned. Yes, they merge and they can make, that's because you have to position this below here. And so this is why it's called thermally allowed. Okay. Now, one thing which is very important is don't get stuck. Because here I call it 1, 2, 3, 4. You can call this 1, 2, 3, 4. Again, let's say I use this one here, and I don't like the colors. I mean, can this be black, black, and this be white, white? It can, right? As long as you have white, white, black, black, it doesn't matter from the left to the right, yes? So, I mean, you can move them around, but no matter how you use them, or if this big black and this big white, the fact is they get aligned. I mean, let's see the spirit, the understanding here. The beginning balloon and the end of the balloon are opposite? Yes. If I make this black and this white, this has to be white and black, right? So that's the point. The beginning and the end, the 1 and 4, they're opposite. And the beginning and the end of this is the opposite. And so they align properly. Doesn't matter how you're going to do it, right? Okay. All right, so that's what we're saying. This is thermoelectric. Okay. So this was what was missing for that part. Then what else was asking here? Yeah, and so now we covered everything. We reviewed like more than 60-70% of the challenging problems. So any other questions? Any issues? Right. Okay. So now let's move on to this. Okay. So if you wanted to, I can always take pictures later on. All right. So now in this problem, since we did the mechanism, we did the transition state, we did the balloons and everything. Here we can just simply see it from a synthetic point of view. Given these reactants, let's say a fast question worth a lot of points, let's say an exam, can you find the answer to this? Well, first thing is to find out which is the diene. Don't you agree this should be the diene, right? Right? Double, single, double. Makes sense? Everybody should know this. And where is the dienophile? It should be this one here. Yes? Correct? Okay. So, what about the diene? Does it have substituent? It has this, it has this, and it has this. Right? Okay, now it's tricky because, it has 3 blue ones, right? And where it's going to be. But so let's first of all we know that let's start with this part. I mean, this is gonna for sure be there, and we know for sure it's gonna be this. So we know that much, yes. If we know that much, that's gonna be the green part here, and we know that again. I don't want to make mechanism because many times you guys put arrows, and of course I'm not asking for arrows. I'm asking just let's do it verbally, mentally, because but this will attack this, right? Yes, remember that? This will attack here. And then, of course, this is going to be this. And, of course, this is going to attack this. So it's going to be a green line here. And, of course, we know that this is going to collapse here. And that's this. So we've got the backbone, yes? All right. Now, let's say, that this attacks from the bottom. Okay, bottom. Dienophile attack. Again, we need to put that word. Dienophile attack. Attack from bottom. Okay. You see, if somebody asks this question, the simple answer is just put a star, right? I mean, actually, let's do this because we have space. So let's do the simple answer. Here's the simple answer. This is here. This is here. This is here, and then this is. Let's do purple, this one here. Okay, you're done. Right? But, in order to be correct, you have a star here. That's a Carl center, that's a Carl center, and that's a Carl center. Do I put a Carl center here? No. Oh, very good. So I have this. Yes? You're done. But however, if somebody asks you for a stereochemist, and sometimes, that's enough for the answer, but, let's see, because it's not going to take too much to practice a little bit with the stereochemistry. Well, but what does this mean? If this, sorry, so if you want to do it with stoichemistry, we're going to copy this here. And let's do it over here. Okay, and then we say like bottom attack, but mean dienophile, right? And then top attack, right? So let's do the bottom attack because we do this extensively, right? We do bottom attack. What is the CN? Dash, yes. Okay, and what is okay? So let's just do that. So that's a dash. And does this stay as it is? It does. Let's do the easy part, right? Attack from the bottom is going to be a dash, and that's going to be. It's not going to double bond. There's no dash or wedge here. Yes. So what about those?
Yeah.
So these, we said that if they were in, that's how we talked about this, right? They would be wedges. So these are out, out. They should be dashes, right? Okay. And now, after you spend like a minute or two, like in 10 seconds, in 5 seconds, you can do the top attack. What's going to be? Let's see. The opposite, right? So this is going to be wedge, and what's going to be on the blue ones? Wedge, and wedge, and you're done. Yes? Alright? So it's not 4 possibilities, it's only 2 possibilities, and that's how, you know, what we did before it helps us to figure it out. Okay, so let's do the other one, and here you see this is the model that helps quite a bit. So let's find, by the way, I mean, this is called the diene, and this was the dienophile. And I hope the same thing we can say over here. Oops, we can say over here. This is true for this. Okay, and over here. And this is the dienophile. Yes. Okay, let's find the backbone. You agree to this one here, this one, this one, this, and this. Yes. And then what is the backbone of the? This is the dienophile, yes? Okay, so this is the substituent. And you agree this is the substituent? Actually, this is a model we used before, yes? Correct? And then this one here is the electron withdrawing group. Okay? Still, the reaction takes place between the red and the green, right? Okay, so let's do this, the product again. So here's the product. So what is between, again, if you want to do 1, 2, 3, 4, and I hope you know, if you have done this here, 3 and 4, this was 1, 2, 3, and 4, right? And you know, here we said it, 5 and 6, and it's 5 and 6, okay? Something else we didn't talk about in the beginning. Here, when you have so many products, the question is the following. Does it matter if the CN is here? Can the CN be also here? So compared to this, that's a 1,4 product. Compared to this is 1,2 product. But you might, you know, here's a 1,3 product, right? But there's nothing else we can do, right? I mean, you know, that's it. If you flip it, and the CN was here, so let's think for a moment, okay? So it was over here, then it's going to be 1,3 to this, 1,3 to this, or the 1,2 here. I think that's a little bit better, right? Because, okay, what is acceptable is 1, 2, so let's do a little bit of account keeping here, because this is 1, 2, it's also 1, 4, and it has a 1, 3. Let me show with laser portfolio to understand it. 1, 2 is which one? This is 1, 2, yes? Next to each other. 1, 4 is this and this, yes? This is 1, 4, yes? And 1, 3 is this. If, let's mentally put it over here. Let me see if I can do it without messing it up too much. Gently, so we can. Okay, good. All right, so if we have this situation, I think what I have is 1, 2, 1, 3, and 1, 3, right? 1, 2, 1, 3, and 1, 3. Right? I think the second case is not as good because it has 1, 3s are bad, right? The first case is better, yes? Right? Boy, did they give you a harder problem on Tuesday, right? On this one, yes? Although they have a harder problem on number 2. So like, that's why it's good to blend them, right? Okay. Huh? Because of the resonance thing, right? You know? So we don't have to do the resonance here because we spent time on the second one, right? Okay, so so for the resonance, we did the one. So problem number 2, we did the 1-4 product, or the 1-2? We did the 1-4. But usually have the 1-2, and neither one has 1-3 because it doesn't work. Okay, so again, that's why it's nice to practice with both. Okay. But let me put it back correctly. That's scary. Okay, so let's do that. Okay, let's go to the bottom. And so this is it. So what do we know is going to happen between, okay, here's 1, here's 2, 3, and 4. What happens between 2 and 3? Double bond, right? Yes? I'm sorry, don't take the next exam. If you cannot answer, I mean, if you answer less than 5 seconds, then we're in trouble, right? So, between 2 and 3, when you have the die-in, right? You create a new double bond, yes? And we did this like, how many hours? Alright, so, I hope it didn't scare you. Take the exam, please. I know you can do it, just relax. Don't be Okay, so now let's go to take the green part right here, yes? So between, and let's put numbers here, this is 5 and 6. So again, this 5 and 6 has nothing to do with before because I flipped it and did it, whatever. Okay. So now, by the way, here I have this thing here. This is the line here. And I have this. So if I have this here, let's do it like this. And let's clean it up a little bit here. So for this actually, when you have a cyclic system, it's really hard not to do the structure. Okay, let's see. You see, that's the problem. Okay. And all right. So let me actually continue on the next slide for this because it's going to be very easy to do it. Oh, there it is. Okay. So the second problem, I'm just going to continue very fast here. Okay. So there it is. Okay. So we have. There it is. All right, so we have this system here. We have this and this. Okay. And so, again, this is 1, 2, 3, and 4. And this is the other molecule. And we have the purple bond, so to speak, it's over here. All right. So when we do the product, the red backbone stays there. Okay. And then between 2 and 3, you have a new bond, right? Okay, that's for sure, right? So now this one here is the blue part, right? Okay. And now we have the green one here. So let's say this is 5 and 6. So between the red one and the green 5, there is a red or a green bond. Right? There's a red bond, yes. Between the green 6 and the red 4, what bond is there? Green, right? Yes. Okay, that's the 6 and that's the 5, yes. Right? And then the 3 and 4 red bond became a 2 to 3 double bond, right? Yes. Okay, so one more time. Again, I don't do the arrows because again, this is a question without arrows. Again, these connected here, 1 to 5 here. The 5 to 6 is double bond come here, and then this collapse over here. So this is so we have this over here, and then we have the purple one over here, right? I mean, we have the purple one over here. Yes. All right. So according to do this, so you're gonna do a dash here, right? Yes. You're gonna do a wedge here, yes. Right. Now what's going to be in 3? Nothing. 3 is a double bond, it doesn't matter. Yes. So then What is the other product?
The opposite.
The opposite, right? So the opposite would be just do this, and do this. The mirror image, so to speak, right? Yes. And then you have the green, this one, the red, this one, the green, this one here, okay? And then you're going to have the here, this one here, coming away from that triangle. So this okay? And so it's going to be the two attributes, yes? All right. So I suggest that you look at the other problems because this is a cycling, the other doesn't have cycling, and so forth and so on. Now, if you look at the blue and the purple, of course, I forgot to put the purple one first here. I forgot to put the double bond. So the purple and the blue, since the inside blues are symmetrical, doesn't matter. But the purple and the blue, they not really blue here. It's there. That's what I mean. That's what I'm drawing now. So it's positions 1 and what? That's 1 and 4, right? This is 1 and 4. The purple and the blue are 1, 4, 1 and 4, right? Situation that's acceptable. Okay. This is 1, 2, 3, 4, 5, 6, 7. Okay, good. All right. Any questions, please? Right. So again, we did the structure of the data doing synthesis. Yes. Okay. By putting it as a dash, you know it's following the other, right? I mean, obviously, I can draw it better, but I don't agree on the drawing because somebody would say put a little bit below here. By putting a dash, that doesn't mean it really goes below. Well, here is a wedge because this is attacked from the top. So when we teach the younger rule, I use the idea that the inophile comes from the bottom to see that it was saying always deal with the bottom and then scratch paper and then do the opposite from the bottom. I hope you agree there's a mirror image of this. Okay. All right. And another way to see that this is pointing away from this blue triangle because that's the opposite for this balloon. Okay. So let's see the question number 4. So this is exactly the same idea, but now it's going backwards. So now this is more challenging, and this can be like very simple. A few many questions can now be worth a lot of points. So given now you have to take this and dissect it. First of all, if it's a Diels-Alder, the first thing you look is for hexagon, right? Here's a hexagon. How do you break the hexagon? 5 and 1, 4 and 2, or 3 and 3? 4 and 2. So you need to find 4 carbons here and 2 carbons in the row. Yes? Right, so let's see. We can have this carbon, right? And we can have this carbon. We can have this carbon and this carbon. Those carbons must have the double bond in between them, yes? Between 2 and 3. And then this can be the green carbon. So if you have this situation, but let's see if let's play around with this a little bit and see. Tell me, I'm going to put X's. Here's another possibility. Okay, so one possibility is to have 4 red dots and 2 green dots. 4 red dots means diene. 2 green dots means a dienophile, or have 4 red X's, because the 4 red X's still have a double bond between them. Yes, makes sense? And the 2 green X's have 1 double bond, right? So these are good possibilities, right? Both of them will work. Which is better? 4 red dots. They have 2 donating groups, and then the other one has 1 donating group. If you both will work, so let's see. First of all, when you have Diels-Alder, you must have only 1 double bond. Yes. The extra double bond must come from what? Triple bond. So if you had the triple bond and it was the red dots, it would not work.
Yes.
With triple bond and you have a
Huh?
triple bond
The,
and
the 4 red dots?
Go for it.
No, but the dienophile.
Your dying is
Yeah,
not
so actually draw it.
Dienophile.
Actually, I create this problem. It's a
Your
challenge.
dying.
So again, let's let's do the possibilities here. Let's do the possibilities here. So, all right. So let's see. One possibility would be. No, I mean the 4 red dots is what comes naturally. That's what I think is the natural thing. But it's play around with that, right? So, okay. So here's one possibility.
There's X is that
Right? And this is one possibility, plus this and this. Okay? Right? That's one possibility, yes? And what is the other possibility? Or is the other one with the
both X
having this one here, let's see the okay. And having this. Don't you agree that's another possibility? Yes?
Does it matter if the substituents are facing? Does it matter if the substituents are facing inward? Because it
Yeah,
doesn't.
yeah, we're going to get to the substitutes, but I'm saying the backbone. Do you agree that this is one possibility, both possibilities are possibly feasible, right? Yes?
Not that matter.
Because, here again, so let's make this green one here. Okay, so if you do this, the first one here, again, let's see if this takes place. So this will come over here. Again, and let's put colors here so you can orient yourself. So that's that. And actually, let me put color over here.
The right isn't. The right one. I'll take the.
It's the right.
All of that, you're gonna have two double bonds that are not equal.
Okay. So that's and then make this red. So let's do that because again, it's really if we have too many colors, it will be confusing. So let's do that. And let's clean it up.
It's the same thing, it works.
And do you agree that this is let's call this A plus B, right? Give me C, right? Again, I mean actually, yeah, let's call it C. That's fine. Okay, so do you agree A plus B? Let's use the laser pointer to follow through. So this will come over here. So that's going to be a bond. Let's make this a red bond. Okay. Then the green one will come over here and connect this. That's a green bond right there. Right? And then this one will collapse and exit. So this works fine. A plus B will give you this. Makes sense? Right? It's fine. It's just 1, 2. Like this. Of course, this 1, 3, but it's not a choice, right? If the purple is here, here's the same thing. So definitely A and B will work, right? And that's what naturally would happen. Yes. But let's give that a try. If that's the case, what would that give me? Let's put that play over here. So, you have this. And again, let's put colors here to see this and then this. Okay, so if we do this kind of thing, and right, yeah, we'll have this, and the double bond will be here, right? So this will come over here, the green one will come over here, and then this will be over here, right? And also that's a possibility, right? So this is also C. Let's see if this is going to change anything in terms of structures. Let's do this one. So this has, I mean, again, this doesn't ask us what attack it is, but if you just look at these wedges and dashes, do you think this is attacking from the top or the bottom? So it's very good. C from A and B is from top, right? Yes? Because if it goes from the bottom, and these are outside, we said it's going to be dashes, right? But of course, you know, if these are like this, they're, you know, wedges. Okay. However, you're going to say, what did you put inside?
No,
Which is actually good, yes.
but if it's attacking from the top and you have a substituent on the diagonal file, shouldn't that be a wedge? And put over there in the product is
But
nothing?
let me, we haven't finished yet, so let's see. All right, so one thing at a time, let's see. So this works out, right? If we have this, in other words, if you have this, is it possible to get this? At least for the red part and the blue part, we're fine if it's attacked from the top. Because nobody told us where it attacked from, right? We did, you know, is that possible? It is. And then, of course, so this comes from the top, it's fine, and then, you know, this is not even from the drawing group, so it's not as efficient reaction, but we have this. So A plus B can give this, yes, we will also give dashes, and so forth, but that's possible. But what's your question regarding just this?
Yeah, so basically, you know how you said that the rule is for the withdrawing group when you attack it from the top or the bottom?
So you talk about the purple on B?
Yeah.
Yes.
When
Which, by the way, is that a good group to have on B? No. But so it's not as efficient reaction as the other, right? I mean, because it'd be nice to have an electron withdrawing group, yes. Okay. But continue, yes.
So if it's not a good withdrawing group, you don't have to do any wedges or dashes on
No, I mean, you cannot do wedges and
Oh,
dashes
yeah.
because it's on the double bond. The question is like,
Yeah.
if somebody asks you, is that a good result to do? Compared to the previous one, this is not as good because you have, but of course you have donating groups on the other one.
That makes sense.
Okay, so, but that's fine tuning. Let's close the parentheses. But is
Yeah,
that
so
possible,
both
A,
kind
B,
of
to give you
works.
C? The answer is yes.
One to the top.
By the way, that's why all this discussion, right? We want to train these ideas and really, and you don't have to study at home, but keep saying this, right? I mean, study at home, but study as much at home because we really exhausted the subject.
So-
So what about if D and E react, right? D and E.
Yeah.
Let's see if there is anything crazy about D and E. We said, you know, this portion, which represents this. I mean, we did it over here. D and E gives me, you still see it, right? I mean, it's the same thing as this. So this portion is here, this portion is here. This doesn't change, and you know, and then you have this thing here. So that's a possibility too, right? Yes. Question.
Can you have A and B attack from the bottom also?
Yeah, and B.
Make it inside.
Yeah, so that's another possibility. So in other words, my point, can it also be this?
Same thing for D and
Can you have this? Is that an acceptable answer? The answer is yes. Correct? Now, is this an acceptable answer? Is this a good multiple choice question? Yes. So in other words, if you have 4 choices, at least you know 2 are wrong. And you say A and B are acceptable, C and right, you can see that when we're doing here. So sometimes in a multiple choice question, it encapsulates all of this. So you don't have to worry. You just do it, get the correct answer, go home. All right. So this is bad, right? So in other words, correct answers are this. That's correct. This is correct. Because nobody asked you whether that's from the top or the bottom, right? These are the possibilities. Okay. Very good. Well, actually, that's right. You know, because or, you know, so this. Okay. Let's do it because we spent so much time, and then we, you know, because this is nice. So, Okay? So it's good to have this, as a good thing of one of the four possibilities that this is. Okay. All right. I think we exhaust this topic enough, right? Okay, so let's look at this now. Okay, so this one here, again, now that I think about it, I gave you more difficult questions than Tuesday, because I guess I ran out of ideas, so I had to do something more exotic. Okay, so this one here has two double. If you have one double bond, it's easy, right? But if you have two double bonds, that's an issue, right? So, how do you do that? Well, actually, in all fairness, Tuesday there is also something like this. So here you have a double bond, and the issue is like which one is which, right? So you have to find the hexagon. First of all, let's start from scratch. If somebody gives you the product, what are you looking, geometrically speaking? Right? You look for a hexagon, yes? All right, so that's easy because I would make it easy for you. Well, no, a hexagon is that half the answer. Hexagon that has a double bond. So this ring doesn't count, this counts, right? So this must be right here, I must separate it into two parts. 4 reds and 2 greens, right? Yes? So either the red is, let's try and play it like this. So either the red is this, and this is the green. I mean, there's only 2 choices, right? Yes?
Yeah.
Right? Or, let's do the other way around. Oh, I mean, we have space here, let's do it this way. And then, or, again, just a second. And then, of course, so let's do both. Okay? And then there's the green. And of course, if it's 2 double bonds, what does it mean? There's a triple bond someplace, right? So the green used to be a triple bond, right? Or, here's the other option. Here is the red now, and here is this. Yeah. It is the product. And then this is the green. Yes? Which one will look better? Either. So, if it's the product, let's see the possibilities. Let's see this possibility. So if that's the possibility, let's see what we have. We have this. We have this, we have this, we have this, yes? And if we have this, then we have a triple bond right here. Right? Okay? Because what's happening is, by the way, and by the way, what is this? This is a string, right? You took a thread and you connected the red and the green, right? So if you take a white out, so to speak, so if you take the white out, and you make this disappear, just erase it with an eraser, let's erase this whole thing. That's the simplest deal done, right? This, right? 4 red, 2 green, connect, double bond done, right? So you can do, that's what I'm doing here. So, let's see, if you do this, right? And then this and this, you call the ring, that's it, right? So the only problem is that we have a shoestring, like some string, which is right here, and let's put it there, and it should not bother us. And again, this is something that students sometimes say a very easy problem. It just looks complicated because that's called what? An intra, not inter, just intra, within the molecular reaction, yes? So I think that takes a check mark, that works, yes? That's fine, that's working, right? So if you want to do, to see this reaction, I mean, you want to do colors, I mean, that's, the red bond is going to make a bond here, so what color is this, right? And so what is this color here? I mean, this collapses here, makes a bond, right? So that's this, green, and then of course, what happens here, this collapses, make the red bond, and that's it. So this works fine, right? So what about here, would that work? Well, I mean, let's do, actually, let's, practice. It doesn't have to be always the diene on the right and the other on the left. Since I do it like this, so let's have it like this. Okay? And then you have this one here,
Just
right? And again, this is a shoestring, so to speak, connecting it right over here, yes? And of course, what happens is that this one, I'm sorry, triple down. So this, what happens here is that this comes over here, this collapses, right? And and then this comes over here. So according to this logic, this should be green, right? And then this should be red. And then the other thing is just sitting on there, right? Yes. Correct? Let's make sure we don't break any octets though. I think that's fine because here we have 2 H's, 2 H's, 2 H's. Here there must be just a hydrogen, right? Yes. And then here is 1, 2, 3, 4, nothing here, and nothing here. Yes. Which one do you think will work a little better? One.
that one. The one you just wrote.
Most people like the top because it looks easier. It looks cleaner.
But this one has no electron donating groups on the.
Which one? This one here?
No, the bottom.
The bottom?
Has no electron withdrawn.
Yeah, so this one here is the alkene has an electron donating.
So that's bad.
So it makes it a bit bad. This has nothing, so it's neutral, so to speak. It'd be
So
better
it's
if it has an electron withdrawing group. So let's look from the green part. This is a bit better. This green is not as bad. That's bad because there's an electron donating close here, right? Let's look at the red. The red has electron donating, yes, and that's good. But here is electron donating too. That's good. What about SCs against
S's.
Well, this can float around, but this can float around a bit more. Yeah, it doesn't look, So this is a bit better because of the green one. But think about the molecule that this actually locks it in an SCs. That's even better, right? So again, this is a discussion to think what sometimes can work a bit better than others. But at this point, I would say both of them are accepted. Pretty good, So exam question, I will accept you.
I win.
Huh?
I did it better, right?
You did it better.
Half a point?
Huh?
Half a point?
No, you did it because of altruism. This is what it is. But you got to have a point earlier for something. Any other questions? Alright, so let's continue with the last problem. Okay? Alright?
Leave it to that. Yo, we use the reduction of the extrapolation.
You want to do the rest? The rest one we should do first. I know you enjoy it very much. So let's put
Yeah, boy. No, thanks for that. So we'll finish this at 5:15. We'll take a break till 5:30. We won't start till 5:30.
Could we just start? Could we just start? Let's just start.
Left.
Can you pause for that?
Oh, it is right. Yeah.